Okay, moving on through the chapter, we're going to continue talking about pulmonary diffusion. Okay, we talked about it on the last recording. We're going to get into a little more detail now about something called Fick's law of diffusion. And it's very simple. Basically, Fick described the factors that affect the rate of diffusion. Okay, so V gas is the diffusion rate. Okay, and so Fick explained the factors that affect diffusion rate of a particular gas. So what are the factors that result in a gas diffusing faster or diffusing slower? And like the factors that affect peripheral resistance, remember peripheral resistance is length times viscosity over radius to the fourth. And basically what these factors are the factors that affect peripheral resistance. This formula here is a similar formula, and it describes the factors that affect the rate that gases diffuse, and it's actually pretty, it makes a lot of sense. So there are three factors here. There's A, T, D, and P1 minus P2. A stands for area. Okay? And so this is the diffusion area. And you can see in this formula here that area is directly proportional to the gas diffusion rate. Okay, so what that tells us is that if there's more area, you're going to have a greater diffusion rate. Okay, and the area is the area of the respiratory membrane or the diffusion membrane. If you have more area to diffuse across, you can get more simultaneous diffusion, and therefore diffusion can happen very quickly. Remember that I told you that our lungs are made up of 300 million air sacs called alveoli. Okay? If the lungs were just two big air sacs and you were to open them up and lay them out, you wouldn't have a whole lot of diffusion area. But the lungs are built for maximal diffusion rate, and that's why instead of having two big air sacs, we have 300 million tiny air sacs. So that if you were to take all the alveoli and you were to open them all up, lay them all out so that you could see all the diffusion area at once. Sorry about that. Minor dog fight. And you were to lay them out, you would see that the area would equal about the area of an average tennis court. So diffusion area is very large, and so the lungs are built for optimal diffusion. Diffusion area is not something that typically changes because the alveoli are there. You know, you're not going to gain more alveoli. You can lose alveoli with damage and smoking. We'll talk a little more about area now later, but for now I just want you to understand that if there's more diffusion area, the gases are going to diffuse faster. Alright, so the second one that we're going to talk about is something called the diffusion coefficient. Okay, D. So D stands for diffusion coefficient, and this is a constant based on the gas. So every gas has its own diffusion coefficient. So oxygen has a diffusion coefficient and CO2 has a diffusion coefficient. That's D. Without going into a whole lot of detail because it's not important at this point, the diffusion coefficient has to do with the solubility of the gas and the molecular weight of the gas. So basically, if you have a higher diffusion coefficient, okay, you're going to have faster diffusion rate. Okay, so it's advantageous to be more soluble and to have a lower molecular weight. That's going to raise the diffusion coefficient and allow the gas to diffuse faster. Okay, so if you look at this drawing here, you have two arrows. You have oxygen and CO2. And the reason why the CO2 arrow is thicker than the oxygen arrow is because the diffusion coefficient for CO2 is 20 times higher than the diffusion coefficient for oxygen. Okay, so basically what that means is that if everything else was equal, CO2 would diffuse 20 times faster than oxygen because of its physical properties, which it's not important at this point that you understand the details of this, but just to understand that CO2 diffuses much more easily because of the physical properties of CO2. Okay? So that's diffusion coefficient. It is directly related to gas diffusion rate, so higher coefficient, faster gas diffusion rate. Okay. All right, what do we got next? Next we have T. Okay, and T stands for diffusion membrane thickness. Okay, T, the thickness of the diffusion membrane. And you can see here that thickness is inversely related to the rate of gas movement. Okay, so if you have a thicker membrane, you're going to have a slower rate of gas diffusion. Okay, and that makes sense because if the tissue is thicker, it's going to take more time to get across it. Okay. Remember that the respiratory membrane, which is what we're talking about here, the diffusion membrane, is very thin. It's basically 2 cells thick. So it's built for maximal diffusion. You're not going to get a capillary any smaller than 1 cell thick, and you're not going to get an alveolar membrane any smaller than 1 cell thick. So it's already built for maximal diffusion rate. Okay, so the diffusion membrane thickness is not something that typically changes, although it can change with damage. So again, smoking may damage the respiratory membrane and cause it to thicken, and if the membrane gets thicker, the gases are going to move across that membrane slower, and you can imagine how that would affect exercise. Okay, so the tissue thickness is inversely related to gas diffusion rate. Okay, and then the last one is P1 minus P2, okay, which is the pressure gradient. Hopefully this sounds familiar. P1 minus P2 is the pressure gradient. And it's the pressure gradient across the respiratory membrane. Okay, so if oxygen is moving in this direction, it's because the PO2 of oxygen is greater here than here. Okay, so ignore CO2 for now. I'm just going to use some pretend numbers. If the PO2 on this side of the membrane was 100 and the PO2 on this side of the membrane was 90, okay, P1 minus P2 would be 10, and so the driving force for moving oxygen across the membrane would be 10. If PO2 increased, the rate that the gases moved would be faster. Okay, and there's 2 ways that you could increase P1 minus P2. You could either increase P1 or decrease P2. Okay, so if you increased P1, you would get, let's say, 110, and if P2 stayed the same, you would have a higher gradient, and therefore the gases would move the same. The gases would move faster because P1 minus P2 is greater. On the other hand, if let's say P1 stayed the same, but P2 dropped, okay, we would also end up with a greater pressure gradient and therefore a faster rate of gas diffusion. Okay, so the rate at which gases cross the membrane is related to the pressure gradient of those gases across the membrane. Okay, so to summarize, what Fick's law does is it explains the factors that affect the rate that gases cross the membrane. And so the factors that are directly related to gas movement, okay, are the area of the membrane. So if you have a greater area to diffuse across, you're going to diffuse faster. This is diffusion rate. If the gas that's diffusing has a higher coefficient, it's going to diffuse faster, and that's a constant. CO2 has a 20 times higher diffusion coefficient, so it's going to diffuse 20 times faster. And you've also got the pressure gradient. With a bigger pressure gradient, you're going to diffuse faster. And then the fourth factor is tissue thickness, and because it is on the bottom of this formula, it's inversely related to rate. Okay, so in order to increase rate, we would need less thickness. Okay. Now, of these factors, the most important factor is this pressure gradient, because this is the one that we have the most control over. Okay, normally the area doesn't change, the thickness doesn't change, diffusion coefficient is never going to change. So if we want to diffuse gases faster, we have to increase the gradient. And the two ways that we can increase the gradient would be increasing P1 or decreasing P2. Either of those would cause an increased gradient, which would cause an increased gas diffusion rate. So during exercises, you can imagine we need to move the gases faster, and in fact we do move the gases faster, and the reason for that is because the pressure gradients are greater during exercise. So we're going to talk about why that is and how those gradient changes occur.